Log on, tune in, find out. Another good idea from Cambridge.
From the University of Liverpool, and he will speak on the new results in higher Brill-Noether field.
Yeah. So I want to talk about some recent results on constructing some rank 2 bundles, which in a certain sense have they have a certain number of sections, but their degree is rather smaller than one might expect for them to possess that number of sections. But first of all, I want to this seems to fit into quite a wide pattern of ideas, and I want to say something about that by way of background first. So, C throughout will be a fixed, smooth, projective curve of genus G over the complex numbers. Complex numbers I don't think matter very much, but for definiteness. So the first overall section I'm calling background, and let me begin very briefly by recalling some facts about classical Brill-Noether theory. So we consider the Jacobian, or consisting of line bundles of degree D on the curve C, and within that the locus, which is denoted classically by W D k minus 1, and I prefer to denote by B 1 dk, and that is the line bundles in J D C for which H naught of L is greater than or equal to K. And there is a number which I will denote by beta 1 dk, and classically this will be rho k minus 1 d, and that is the number, well, the number is G minus K into K minus D plus G minus 1. And this number represents the expected dimension of this as a sub-variety or sub-scheme of JD of C. The classical ideas on these things come from Brill and Noether in the 1880s, but were sort of fully and properly worked out in the 1970s and 80s. But I want to remark on a couple of points about it, just a couple of points here. In the first place, that every component of B1 dk has dimension greater than or equal to beta 1 dk. And secondly, that on a general curve we have equality here. And in particular, B of 1 dk is non-empty if and only if beta 1 dk is greater than or equal to 0. There's a good many other results about this, but those are the ones I just want to mention here. Okay. Now I want to actually I like to be considering rather more not general curves, but when we come to the constructions, they will be not general curves. You'll definitely be special curves. And so let me say something about ideas in that respect with respect to line bundlers. For any line bundle, I can define gamma of L to be gamma of L is the degree of L minus twice h naught of L plus 2, which may be called the Clifford index of L. The Clifford index then of C is the minimum of the gamma L for, well, let me say h naught L greater than or equal to 2, and I think I will put in here the several possible forms of the condition. Let me say degree L is less than or equal to G minus 1. And the classical results are such things that, cliff C is always greater than or equal to naught. Cliff C is naught if and only if C is hyperelliptic. And there are other descriptions of things. For low values of cliff C, the curves are known. For higher values, they're not completely known. But the particular comments I want to make are that for the general curve, cliff C is equal to the integer part of G minus 1 over 2. And there's one other thing I want to say. I want to define also there is something closely related to the Clifford index called the gonality. The gonality of C is the minimum of the degrees of L for which h naught of L is greater than or equal to 2. It follows at once from this that the gonality of C is greater than or equal to cliff C plus 2, and we have equality on the general curve, and lots of other curves as well. Lots of special curves for general C. In fact, rather more remarkably, it turns out that the gonality of C is always less than or equal to cliff of C plus 3. That seems a rather strong result, and but it is true. Okay, so I want to make some other remarks, very briefly, some other remarks. The first point is that this is closely things to do with this are closely related to syzygies, and in particular there are relationships with causal cohomology. And causal cohomology provides conjectural formulae for cliff of C and gon C in terms of non-vanishing of certain cohomology, causal cohomology groups, and the two relevant conjectures are the Green conjecture and the Green-Lazarsfeld conjecture. I won't go into details of these. But just to remark that they've been proved now in very many cases. Particularly the Green conjecture has been proved in lots and lots of cases. And the second thing I want to remark is that there is a relationship with, not entirely independent of this, with curves on K3 surfaces. this will come in rather later on to my discussion. This, I think, goes back to ideas of Mukai, Lazarsfeld. A lot of people have done things on this, and Voisin did a lot of work related to this and relating it to causal cohomology and so on. And it's involved in Voisin's proof of the generic green conjecture. However, that's just by way of some of the setting for the problems I'm talking about. Now, I want to elaborate on something here. And I wanted to discuss, again, hopefully reasonably briefly, the slope conjecture. So here we will have mg is denoting the moduli space of curves, of smooth curves of genus G. And mg bar, the standard compactification of this by stable curves, so the moduli space of stable curves of genus G. And the well-known fact that the Picard group of mg bar is freely generated by something lambda, which is usually known as the Hodge class, and some boundary things coming from mg bar minus mg. There are various boundary components, and these, I think, are, if I can get them, sure if I can get them numbered correctly. I think they go from delta naught up to delta integer part of g upon 2. And it doesn't matter very much. If I've miscounted them, it doesn't matter very much. Now, suppose we consider effective divisors D. Effective divisor D. Then the slope of D, S of D, is defined to be A over B, where D is equivalent to A lambda minus sigma bi delta I, and B is the minimum of the bi's. And I should say the effective divisor D not containing any boundary divisor. Of course, the delta I are effective, but I don't want those. I want other ones, and they have this form, and there is a minimum value, and this thing has a minimum value, or at least an infimum, which is strictly bigger than 0. So that's defined. That's the slope, which we should call SG. It's the infimum of S of D, and it is strictly positive. Now the question is, to try and measure this slope, you can consider possible known divisors. And in particular, one can define the Brill-Noether divisor, which I seem to be writing as BNRD. Yeah, which will mean the curves, or the classes, the curves. No, this is within the genuine or smooth curves, MG. BNRD is C, the curves C, for which the Brill-Noether locus, which I'm wanting to write B1, I suppose, B1 R plus 1D is non-empty. Sometimes that will be the whole moduli space, sometimes it'll be empty, and in between, of course, is the interesting.
But B1D R plus 1, could that, might you transpose?
Sorry, yes, I've transposed these things. Apologies. I hope I've done it right over there, yes. Okay, now if, well, I seem to be changing notations a bit here, but if beta of 1 dk is equal to minus 1, sorry, then B, and now I'm doing what I would normally do, I'm replacing the R by k minus 1 here. Then Bn k minus 1d is a divisor in Mg. I mean, I think essentially this condition means that the codimension is less than or equal to 1, and it is in fact true that because this is minus 1, the general curve has this empty. So the general curve is not in it, so it's a genuine divisor. And it does not contain any boundary components, I guess. Well, sorry, this one doesn't anyway. I want to take the close. This one doesn't contain any boundary components because it doesn't. It's contained in the complement of the boundary. So I want to take its closure, which is then is also a divisor in the whole space, and then the slope of this has been calculated. Well, let's take k minus 1d. The slope of that has been calculated. Let me see. It's actually independent of the numbers. It depends only on the fact that this is minus 1 and not on what d and k are. And it's 6 plus 12 over g plus 1. Now this can only happen, if you look at the formula for this can only happen, in fact, if g plus 1 is composite. So it can, the divisor is, the divisor exists only if g plus 1 is composite. Just for numerical reasons. That's just an observation, but we have in any case then, arising from this, we have the slope conjecture of Harris and Morrison in round about 90, that SG is greater than or equal to 6 plus 12 over g plus 1 with equality equality only if g plus 1 is composite. So that was the conjecture. The sort of general idea was that there was some sort of feeling that these Brill-Noether loci ought to provide things of relatively small slope somehow, and so therefore these we would guess that these, I mean there are other possible divisors you can identify which have bigger slopes, so it seemed not unreasonable. However, it's not true. Not it. And counterexamples began by being discovered by Farkas and Popper in a paper published in 2005, and there have been others since then, but let me just describe this one quickly, where it comes from. We have g equals 10, and they then define the following divisor, kg. Well, the simplest way of describing it is to take the classes of the curve C in MG, for which C is contained in a K3 surface. And it turns out that it turns out that if you can work out the slope of this thing, and it turns out that the slope, or rather its closure, of K10 bar is 7. And 7 is less than 6 plus 12 over 11. So that's the first counterexample to the slope conjecture. Then Farquhar has since then, particularly Farquhar has discovered a lot of further whole classes of counterexamples in different genera and so on. Right, where shall I go now? Back over here perhaps. Now, what I want to just, I think we can do this. There are alternative descriptions of K10, and these some parts are relevant to us. Well, I don't know whether, maybe I won't give them all, but ones that they go, there's one in terms of this, which is basically the non-surjectivity of the wall map. Perhaps I won't write that one down because I'm not specifically using that, but you can also describe it as if you take the relation, we begin the relationship with rank 2 bundles here, which is why I want to state this one, but these are rank 2 bundles of determinant, canonical determinant, and it just turns out to be 7 sections in this case, and that, to take that non-empty, turns out that that gives you the same thing as C being contained in a K3 surface. I'd also like to rewrite this because it's relevant to what I'm going to say later. It's also C contained in P4, so it has an embedding in P4 with degree of C equal to 12 and C contained in the quadric. And just to fit in with some of the other ideas I've had, just using the definition of causal cohomology, you can make that K11 of M is non-zero for some M in B112.5. The 12 here is the same as this 12, and the 5 is 4 plus 1. So I mean, they do have there is some linking between the numbers, and if you just write down the definition of this cohomology group, it turns out to be exactly the condition that the embedding of the curve by this M is contained in the quadric. Okay, so those are some descriptions. There are others. But let me move on. Otherwise I won't get to where I want to get to. So section 3 then. I want now to move on to more things to do with higher rank bundles, particularly rank 2, but higher rank Clifford indices. Well, let's take MND to be the moduli space of stable bundles on C. BNDK will then be the bundles E in MND such that H naught of E is greater than or equal to K. So the corresponding higher rank Brill-Noether locus. And beta ndk, you work out what that should be in this case. The expected dimension is n squared into g minus 1 plus 1 minus k into k minus d plus n into g minus 1. Well, do the things for rank 1 generalize? Well, the answer is that one thing does, and most other things do not. But in particular, every component of B ndk has dimension greater than or equal to beta ndk. This, incidentally, says nothing about whether this thing is empty or non-empty. I just say every component. There could be no components. And the second point is simply to say that there are no results for general C of the type B, N, D, K is non-empty if and only if beta NDK is greater than or equal to 0. All logically possible combinations of the two sides of that are possible. Okay, so what can we do in relation to some of the ideas I discussed previously? Well, we can certainly just define cycles, Bn, which I'll write as Bn ndk, which will be the curves C in Mg, such that B ndk is non-empty. And then we take to close that up, B n ndk bar in Mg bar.
By no results, you mean it's false?
It is false in both directions, as stated there. Of course, if I fix particular values of ndk, the answer may be known. But there are examples where beta is negative and this is non-empty. Examples where beta is positive and this is empty. So so that's what I mean by saying all logically possible combinations actually happen. Right, now let's take, I've been concentrating mostly on the case n equals 2. These can be defined as cycles, always. The question is, could they be divisors? Well, for n equals 2 at any rate, the expectation is one can't have minus 1 here if you just look at the formula. But so the first negative number you can have is actually minus 3. And if that's minus 3, one might expect this to be a divisor. Of course, this comes with the statutory warning that anything expected in higher rank Brill-Noether theory is probably false. So let me not say too much about that. There will be, I'm going to give examples where it's true, but that's another point. Okay, but the thing I can go on to do, I think I'll take another board for this. So there is a possibility of constructing divisors. That's the point. So what I can do anyway is to define the Clifford index, and that's defined in exactly analogous way. So this would be the degree of E minus twice. It will not be that. It will be the degree of E divided by the rank, which is n, minus 2 h naught of E divided by the rank, plus 2. That turns out to be the analog of the line bundle case, the natural analog. And then we define now, there have been cliff n of C to be the minimum for E in M, not in M, ND. So for E semi-stable, sorry? I thought somebody said something. Minimum for E semi-stable of rank n, degree D. Seems more natural to make the definition with semi-stable rather than actually restrict to the stables. One could make it for stable. E semi-stable of rank n, degree D, of gamma of E with h naught E greater than or equal to twice the rank, and the slope of E, that is the slope of E, and the slope of E less than or equal to G minus 1.
Excuse me, why do you expect to be a divisor? I'm a bit confused.
Well, I mean, I don't know that I can actually answer that, but if you calculate some dimensions, natural dimensions for things, I think you do come up with this expecting to be a divisor. You have to work in some suitable, not covering space, but some suitable space over the moduli space and then project into it. And if you calculate the codimension, look at the codimension upstairs, you find it comes out as you would expect. Okay, sorry to be not particularly helpful on that one, but if you sort of, it seems, I mean, I don't have the calculations immediately to hand, but that seems to be a natural possibility. But I wouldn't go any further than say that. I think if you, well, yeah, it's not a straight, it is, I mean, even the line bundle case with -1 wasn't completely straightforward, because one didn't until it had been proved that it was on the general curve, it didn't hold. I mean, it wasn't an automatic thing from just writing down a codimension or something to say that that wasn't the whole moduli space, even in the rank 1 case. So it's not an automatic thing at all, but this seems to be the right conjecture. Well, I always cover myself by saying that all reasonable conjectures in this area are false. So, doesn't matter what I say. Right, so this was defined in this form, although some things have been considered earlier by Langer and me in, well, the paper is 2010, but maybe I published in 10, but the archive, it went on the archive in 08, 0811 4680, but it is published. And the final thing I want to mention before I actually go on to talking something about the construction is Mercator's conjecture. Well, I'll state it for n equals 2, needs a slight modification for n greater than 2, and this is the paper publishing this was 2002. And again, I think he obtained this result several years before this, or not the result, but evidence for this conjecture several years before, and that is that that is quite simply here for this is that cliff 2 of C equals cliff of C. I should remark, perhaps, that it is always true that the minimum of cliff C and 1/2 cliff C plus 2 is less than or equal to cliff 2C is less than or equal to cliff C. The inequality cliff 2C and indeed cliff NC less than or equal to cliff C is immediate. You simply take a line bundle which any line bundle which qualifies to be counted in the Clifford index down here, and take a direct sum of n copies of it and work it out, and you find you get the same number, and it's semi-stable. And the remark that follows directly from this is that that implies that the conjecture is true, and this is what Mercator actually proved in this paper, or part of what he proved. At any rate, the conjecture is true for cliff C less than or equal to 4. So this means that the first case one needs to look at for this is genus 11. Okay, let's so this is counterexamples to Mercator's conjecture. Well, actually, the first counterexample to be noted was in rank 3, n equals, I'm using n on n equals 3, and that is in a paper by, well, it's actually noted in a paper by Langer, Mercator, and me, which went on the archive in March of last year, and that actually used an old example of Mukai. So the history is a little strange in a way. This example of Mukai hadn't really been noticed, or not by people who also knew anything about the rest of this. And in fact, that example of Mukai predates Mercator making his conjecture. But he only became aware that this example contradicted his conjecture a short time ago. Okay, now the remaining papers that have results on this are all more recent than that. They're all from the last 12 months. So there's been a fairly rapid development of these ideas. And the first point, which doesn't actually produce a counterexample, is in a paper by Zhigorshik, Mercator, and me, which I will comment on shortly. And that's on the archive. All of these currently on the archive, but don't think any of them has actually appeared in print, although several of them are due to shortly. And what we actually described there, apart from, the aim of this was something we'd done years earlier, which effectively gave a new description of the divisor K10. Now, we didn't put it in those terms, but that's what it effectively did. But we only developed that idea much more recently, and there's more in that paper as well. And then we have developments, Farkas and Ortega. Maybe I won't spend time listing the various references. There are 2 papers by Farkas and Ortega and 3 by Langer and myself. And between us, we've found a lot of examples of counterexamples in rank 2. So what I want to move on to then is actually starting to describe them. Perhaps I'll state the basic theorem, which is a slight development of what actually appeared in the GMN paper. I wouldn't say, in a sense, the ideas for this bit were not, have been around for a while. But let me state the theorem, and then perhaps I'll go on to the example. The basic theorem is this theorem. Let M be a generated line bundle of degree D less than twice the gonality of C with H naught M equal to 5. Suppose that psi from S2 H naught M to H naught M squared is not injective. That means that if we use the sections of M to embed the curve in P4, the image is contained in the quadric. Then there exists a stable bundle E. And it's actually stable, not just semi-stable, of rank 2 and degree D, which I've defined, have I? Yes. Degree D on C with H naught E equals 4. Well, you see, if it's if the degree of this were actually equal to twice the gonality of C, then its Clifford index will be equal to the classical Clifford index. So if the degree is less, its Clifford index of this E is less than the classical Clifford index and would give a counterexample to Mercal's conjecture. Now in the paper GMN, where we proved a version of this, this is a little generalization of that, but the method of proof's the same. We weren't concerned with that because we were actually working in the main case we were working in had D equal to this, when the same technique can be used, but the result has to be slightly modified, and we were in genus 10. But so that was a somewhat different situation. But that is what leads to, well, I could make the remark here that psi non-injective is equivalent to saying that the causal cohomology K11 of M is non-zero. So this does give another description of K10 by when you take D equal to this and work through this, it gives another description of K10. But that's, in a sense, a separate issue. So I think I'll leave this. It's not a terribly difficult thing to prove. We gave a geometric proof, and others, I think, have given other types of proof. But since I do want to discuss some actual examples, I think I'll leave that at that and talk about how we use that. Right. Well, I should say that all the examples constructed of rank 2 things, I think that's not, maybe the later paper of functional Ortega uses something a little bit more, but the first paper of functional Ortega and all my papers with Langer use essentially the same idea. And so this is 2, construction of bundles. And theorem. So this is coming then from this work. Result is in our most recent paper. Suppose D equals G minus S, where either S is greater than or equal to minus 1, G is greater than or equal to the maximum of 4s plus 14 and 12, and G is not equal to 4s plus 16. These just come in numerical things in the calculations to get just necessary to, well, it's not absolutely certain that they're necessary, but they are involved at any rate in actually verifying certain things. Or S is greater than or equal to 1 and G equals 4s plus 12, then there exists a curve C of genus G with cliff C equal to the maximum possible value, the general value. So as far as the Clifford index goes, this is a general curve, but it is not in fact a general curve, but it has various special properties, but it's as far as the Clifford index goes, it is, and a stable bundle E of rank 2 on C with, well, the important thing is that gamma of E is equal to G minus S over 2 minus 2, which is the same as saying, given that the degree being G minus S, where's the degree gone? Stable bundle E of rank 2, well, I haven't put it in. I should put in stable bundle E of rank 2, I think, and degree G minus S. That's the same as saying that H naught of E is 4, to say the Clifford index, given the degree, the Clifford index is that. With gamma E. Hence, cliff C minus cliff 2C is greater than or equal to G minus 1 over 2 minus G minus S over 2 plus 2, and that is certainly positive. So it is, all these examples give kind of examples. I'll state a corollary of it. Corollary, let gamma be an integer, gamma greater than or equal to 6, then there exists a curve C with cliff C equal to gamma such that cliff 2C is less than or equal to 1/2 of into the integer part of 3 gamma over 2 plus 1. Moreover, C can be taken to have genus 2 gamma plus 1 or 2 gamma plus 2. In other words, the two genera which give integer part of G minus 1 over 2 equal to gamma. Now, okay, so one may observe from this that this is for large gamma, this is roughly 3/4 of gamma, and we know we have the bounds that are roughly a half gamma on the bottom end, and roughly and gamma on the top end for cliff 2c. So it's about halfway. If a large gamma, it's about halfway in the range of possible values in terms of gamma for cliff 2, or in terms of cliff rather, for cliff 2c. Now, I should remark, but probably won't. Right, of Fox-Ortega's examples, in fact, a lot of the examples constructed here actually just had cliff 2c equals cliff c minus a half. And Fox-Ortega actually did Fox-Ortega actually cover the cases 11 and 12, genus 11 and 12, which are well, they cover 11 with s equals minus 2, which isn't covered by this, and 12 with s equals minus 1, which is also not covered by this result. So their two cases in 11 and 12 are not are definitely not covered by their result, and in those cases the minimum possible value of cliff 2c is cliff 2c minus a half, and that is what they construct. But we get stronger results for higher values of g, possibly roughly equal for 13 and 14 or something, but definitely stronger results for higher values. But the methods are essentially the same. Okay, so in the remaining few minutes, I will try to say something about the proof of this result. These give the ideas. Well, according to the theorem from the previous section, we need to show, or it is sufficient to show, I should really say, that there exists a curve C and a line bundle M on C with the degree of M less than twice the canality of C, and H naught M equals 5, and then psi M of C is contained in the quadric, where here psi M is the natural map from S2 H naught of M to H naught of M squared. So that's what, in order to apply the theorem from the previous section, this is what we need. So how do we construct curves like this? Well, we construct them as curves on K3 surfaces, and more specifically on K3 surfaces of type 2,3 in P4. So that's the intersection of the quadric and the cubic in P4. So then they're obviously contained in a quadric. So that part's now going to be automatic. And we just take the restriction of the hyperplane bundle for M. So one's got to check that all the numbers can be worked out. So the basic thing is that the result, Knudsen has a paper in which there are results on curves, when curves lying on K3 surfaces of particularly K3 surfaces of Picard number 2. So this implies, under our conditions, there exists a K3 surface S with our numbers. There exists a K3 surface S of type 2,3 in P4 containing a curve C such that the Picard group of S is Hz plus Cz, where H is the hyperplane. And we have, following on from that, just what are the relevant numbers, intersection numbers. It's really virtually the whole thing is a matter of calculating intersection numbers. H squared is certainly 6, intersection of a quadratic and a cubic. C dot H is G minus S, because that's what we said it was. The degree was C minus S somewhere, G minus S somewhere or other. And C squared, by the adjunction formula, C squared must be 2G minus 2, because a K3 surface has trivial K, a trivial canonical bundle. So those are the, so one can calculate all the intersection numbers. Where shall I go up here, perhaps? So if D is equivalent to mh plus nc, d squared is 6m squared, of course, plus 2d mn plus 2g minus 2n squared. And what do? We take, we put m, we define m to be OC of h restricted to the curve, the hyperplane restricted to the curve, right, that's the definitions. It remains to show, that gets all the numbers right, it remains to show that cliff C equals G minus 1 over 2. I suppose I haven't actually said that, well, no, that's right, cliff C equals G minus 1 over 2. I think that's what it remains to prove that. That does that bit. And that H naught of OC of H restricted to C is equal to 5. So just some numerical calculations now. The second one is almost obvious, because H is the hyperplane in P4, so certainly on the K3 surface, H naught of that hyperplane bundle is 5. So it's only a question of proving that the restriction map is an isomorphism. Restriction to C is an isomorphism. So that one's pretty clear. This one has a good deal more to it. I mean, that is not absolutely immediate, but it is what you would expect at any rate. And the first problems are that it is that we don't immediately know whether there are effective divisors on the K3 surface which have d squared being either 0 or minus 2. In other words, rational or elliptic curves. So one can actually, under the hypotheses, one can rule out d squared equals 0. D squared equals minus 2, we can't even now quite rule it out. We had a problem with this originally. That problem didn't actually arise in the Farkas-Ortega part of the construction, but Herbert Langer and I did have a problem with it. But we were able to show that not that you couldn't have minus 2, but that any curves with self-intersection minus 2 did not actually come into the computations. They didn't have a suitable degree to come into the computations. So the other ingredient that has to be fed in are, well, we do at some point actually want to know that the Clifford index of C is actually the diagonality plus 2, so it is that which it can be stated also as saying that the Clifford index is computed by pencils, and that requires proving that C is ample on S, and using a result of Ciliberto and Pereschi. And the other thing that's needed is, which is much, the other thing we really need, there's a result of Donaghy and Morrison that says that if the Clifford index, which says among other things, that if the Clifford index is less than the integer part of g minus 1 over 2, then there is a d on S such that its restriction to C computes the Clifford index. And we have to use such a d, because otherwise we don't, if we just take things on the curve, we don't know how to calculate. But if we take things which are given by effective divisors on the K3 surface and then intersect with the curve, then we do know how to calculate. So then there is a detailed calculation. Out of this we get some inequalities, and there is a detailed calculation to show that these inequalities then lead to a contradiction. So in fact the Clifford index is equal to the integer part of g minus 1 over 2. Well, I've come to the end of my time, so I'll stop there.
Is there any question?
Ignacio Sols and I think Thomas Gomez have a slightly, not slightly, widely different approach to this, right? That
Not Gomez,
somebody else?
Solves and somebody.
Sols is definitely there, but I don't know who it is. Take a bundle and then take tensor by line bundles and then look at the loci in the line bundles for a generic key.
Oh yes, yeah, right.
And then there was some positive results.
So you could do that. That's
Yeah.
another possibility.
Yes.
Yeah.
There, things seem to be a little more under control.
Under control. Why are we not under control?
These are, whatever you expect, something, some natural results are true in this case. I mean, I'm not looking at these things now, but so I don't know exactly what I'm saying, but you see. Yeah.
Well, I don't know. I mean, one can. You would mean that they had some explanation for their results. Do you? I mean, you mean they've got some theoretical framework in which
That's
their
right,
results
that's
should give certain answers.
Yeah.
I mean, I think that's true that we don't have that. To some things there is something, but to get all these examples here, no, I don't think for these examples it does. To get things with the Clifford index being a little bit slightly smaller for higher rank, you could I'm sure, formulate in terms of some, no, that's not quite what I mean. What I mean is if this is genuinely, there is a question, is this genuinely non-generic behavior for the curve C or not? And the answer to that, I think, is known maybe up to genus 19, according to Farkas and Ortega. In other words, for the general curve, cliff 2 is equal to cliff up to that genus. But we don't have any other information. Farkas believes that cliff 2 is equal to cliff for the general curve in every genus, but there is no proof. So that is, but this is a possible approach to things. But then the natural thing then would be to say, given that we have some divisors or possibly cycles of lower dimension in the moduli space where certain things happen. But apart from simply saying that, apart from just getting that inequality, I don't really see that we've got a great hold on the getting still lower values of the Clifford of cliff 2. We might be able to get some hold on saying that cliff 2 was less than cliff. But do we have any basis for saying it's much less than cliff? I don't know. I know nothing on this beyond the fact that we now have examples. And then, of course, there's always the question of higher rank still. Of course, the things in rank 2 automatically give results in any even rank. So cliff 2nc. If cliff 2c is less than cliff c, then cliff 2nc is less than cliff c. And incidentally, there are no, as far as I know, there are no known examples, even the ones in rank 3, for curves where the Clifford index is less than the classical Clifford index and the curve does not lie on the K3 surface. So, what exactly is the magic of lying on the K3 surface? I mean, we know it's magic in some ways, but what exactly is the magic?
Assuming that cliff 2 is equal to cliff for the generic curve, can you find the modulus space out of the curves for which it's not true? Because we had, Andrei Hershowitz and myself.
I believe it should be. It may well be possible. I'm not sufficiently. The only things where I know what the divisor classes of certain named divisors in the moduli space are when somebody's worked them out and written them down. I'm not into the techniques at the moment of doing it, so I can't answer that question. But it does seem plausible. I mean, certainly if you have a very specific definition of this, that you should be able to say that if this thing really is a divisor, then its class is so-and-so. It wouldn't automatically prove it was a divisor, I think, but...
I just wanted to check this G minus S, where you get the curve on the K3 with where the S comes in. Does that require these weird conditions on S, or do the weird conditions come later when you do the calculation?
Those particular conditions, but some conditions are needed if one's to use Knudsen's results, but they are weaker than the conditions that we've stated. They come in mostly into the calculation somewhere. For example, proving that d squared is that d squared cannot be 0, for example. You have to decide. That's a relatively nice problem. This is a homogeneous quadratic, and you just want to ask, are there integer solutions? So that's, of course, equivalent to saying that are there rational solutions, and you can give conditions. Something's a perfect square. It just comes down to something being a perfect square. And that is what one does, and some of these conditions come into, that can be a perfect square for certain values. And that is one place where it's used. It's also actually used in these calculations that I haven't said anything about really, where we're actually trying to prove that what the effect of this d. You get these inequalities for this hypothetical d that computes the Clifford index if the Clifford index is not as big, not maximal, those you have to prove those these inequalities have no solution, and certain conditions come in. You know what happens when you try to solve a batch of inequalities. So in other words, there are definitely some of these are necessary for the method, although not necessary for the conclusion. I suspect one can argue, certainly argue around some bits of it. So they may not be true. And I don't totally rule out taking larger values of S and hence getting smaller values of this, but it's not... larger values of G and hence getting smaller values of this. No, I don't mean G. What do I mean? G minus... I want to make G minus S smaller, but since there are conditions relating G and S, it's not quite obvious how to do that. So I don't think it's, I mean, basically what I'm saying there is it's not certain that this has exhausted the possibility of this argument.
More questions? Before we thank Peter, let me say that the program and this day and it had been organized mainly for Peter Newstead. So I would want to take the opportunity to thank him and join me to thank him for the organization.
Bye, Peter Newstead.
Bye, Peter Newstead. Sorry. Okay, let's thank Peter for the organization.
Thank you. Thank you.